So remember that if we wanted to plot the water saturation versus distance, a typical plot might look like this. Okay, so the water saturation is not 100% at the inject. You might be injecting 100% water. The fractional flow would be 1 or 100%. But right at x is equal to 0, the water saturation is not 100% because you do have residual oil. In this case, clearly the residual oil saturation is 0.2. Then the saturation decreases. It's not like a straight line. It sort of looks like a straight line in these plots, but in general it's sort of curved. And at the front distance, xdf, there is a shock front. So the saturation decreases abruptly to the initial water saturation. In this case is equal to the residual water saturation, where it is everywhere in front of that front. And this is at a particular dimensionless time, 0.1. At a later point time, it's 0.3, it's here. And then at a later time, let's say in this case about 0.55, that's when this front saturation, remember SWF is always constant, first touches the producer well. So at XD is equal to 1. We know what that breakthrough time is. It's 1 over the derivative of the fractional flow at SWF. And so we could use those curves to do that. That was 0.55. Remember that the breakthrough time is always, always, always less than 1. Okay. And then above the breakthrough time, the saturation starts to increase. It starts to produce more oil, but you're producing a lot of water as well. And if you were to plot the water saturation at the producer well versus dimensionless time, the water saturation is equal to the initial water saturation, which is equal to the residual water saturation in this case. At breakthrough, which is right here at about 0.55 pore volumes injected, you see a huge increase in water saturation. It'll immediately go up to SWF, the front saturation, and then it'll slowly increase beyond that. Okay, so the water saturation will continue to increase and eventually get to 1 minus SOR. Another plot we can make is the fractional flow of water at the producer well, which is related to the saturation of the producer well, but not the same thing. Remember, fractional flow is a function of saturation, but they're not the same. Prior to breakthrough, we were at residual water saturation. So even though we had 20% water, none of it was being produced. Then at breakthrough, at 0.55, you get a huge increase in fractional flow. It goes above 90% in this case, and then continues to increase beyond that. If we were to plot the dimensionless oil recovery versus time, it would look like this. It increases linearly. It's a 1-to-1 ratio. So when TD is 0.5, the dimensionless oil recovery is 0.5, right? Because the reason for that is that you inject 1 barrel of water, you produce 1 barrel of oil. This is, again, for the case that we are above residual water saturation. Then, after that, you start producing a lot of water, so the oil recovery is low. So you might be injecting, 1,000 barrels of water, but only producing 100 barrels of oil because 900 barrels of water is being produced. So it's a slow increase beyond that. It'll continue increasing. And if you go long enough, that value of NPD will be 1 minus SOR minus SWR. Okay. So that's a summary of some of those plots, and you will have to do some of that for your homework. So up until now, I've mostly been talking about the cases where the initial water saturation is equal to the residual water saturation. And that's a common case, especially if you're well above the capillary transition zone. You've likely learned about that in your petrophysics class. We're going to talk more about it at the end of the day and on Friday. But what if, let's say SWR is 0.2, but SWI is 0.4. Then what happens? Well, first off, if you're above the residual water saturation, then that means that some of the water is mobile. It means it can flow. And because of that, you will produce some water even before breakthrough. So even at the very beginning. So you inject your producer well, you produce both water and oil. It might be mostly oil, but you will produce some water. The other thing as far as calculations are concerned is the breakthrough tangent is not drawn from SWR anymore, but SWI. And what that means is that the tangent, the point of tangency, gives a different value. So the waterfront saturation and the fractional flow of water at that front are going to be different than if SW is equal to SWR. So this is a typical fractional flow curve. Normally what we would do is if SWI was equal to SWR, we would say that we start right here at the residual water saturation, which in this case is clearly about 0.2. We would draw our tangent and find the point of intersection over there to get SWF and FWF, and we would proceed with our calculations. But if SWI is greater than SWR, in this case I'm saying it's about 0.4, then the initial fractional flow is less than that. So that's almost 0.1. So again, maybe you're producing 10% water, 90% oil, as opposed to 100% oil. But then what you do is you take your breakthrough tangent and you start from here, not from over here. So I draw my breakthrough tangent that way. I find the point of tangency. Looks like SWF where it touches is right around 0.65. And the fractional flow of water at the front is about 0.83 or something. Okay, so that's how you do those breakthrough tangents if SWI is greater than SWR. If SWI is equal to SWR, then you start from that place, and you will get a different value because that tangent will look different. It's a different slope. Okay. The other thing that we talked about in last class was the effect of gravity. So the fractional flow of water is given by this equation if there's no capillary pressure, right? So go back and look at the lectures and the slides when the fractional flow of water is less than includes gravity and capillary pressure. In this case, capillary pressure, I'm still assuming is 0, but we have included a gravitational effect. Now there would be no gravity really in two cases. The first case would be obviously if the reservoir was just flat. If the dip angle alpha was 0, then there would be no gravity. There would be another case where gravity could be neglected, and that is if delta rho is small or basically 0. So if the densities of water and oil were the same, then that term would go to 0. Now that's not usually the case. Usually water is more dense than oil, although there are exceptions. It'd be more common that the dip angle would be approximately 0, but let's talk about the case where it's not 0, and many, in fact most reservoirs have some sort of dip, right? And so gravity is important. The fractional flow curves versus water saturation look like this. I've drawn 3 of them. The middle one is sort of the cases that we've been talking about where there is no gravity. So it starts over here and increases monotonically to 1. It's never negative and it's never positive. However, if you inject water from the top, so the flow direction is down, then the fractional flow curve is this top one. And the fractional flow of water actually exceeds 1 at a certain water saturation. And we've talked about that before in the past. The water is more dense, so because of that, water wants to go down, oil wants to rise to the top. And then the bottom one here is for a case where you have you're flowing upward. So you're injecting water from the bottom and it's going up. We characterize these by a dimensionless number we've talked about in the past, which is the dimensionless gravity number. It's a ratio of gravity to viscous effects. Again, if your delta rho is small, then the gravity number is effectively 0, in which case, this middle curve is probably effective. Or if your velocity is really big, okay, and big is all relative, but if you're greater than a foot per day or so, then this might be a small number. But if your density difference is big and or your velocity is small, or your viscosity of oil is small, then this gravity number can be significant. And what that means is, and I'll show why in just a moment, the flow upward of water, if you inject water from the bottom and it goes up, the front water saturation is higher. The derivative of the waterfront saturation is lower, meaning a longer breakthrough time. And that's what you want, right? We don't want early breakthrough, we want late breakthrough. We want that situation where we're injecting water and producing oil, all or mostly oil, to occur as long as possible. So what that means is it's always beneficial to inject the denser fluid, in this case water, from the bottom to the top rather than the other way. So always, always, always you'll want to inject water at the deepest part of the reservoir and inject it up, okay? Have to be a very unique situation not to do that. You're going to get more recovery that way. Again, the effect might be small unless the velocity is small, or or for whatever reason you have a large gravity number. And we may discuss later, but there are other benefits to injecting water upwards. So inject from the bottom, let it go to the top. But let me show you from a breakthrough tangent perspective why it is beneficial to do it this way. So what I've shown here is the breakthrough tangent, and here again we're assuming SWI is equal to SWR, so you're starting at point 2. And SWF, this intersection, is right here, which I think is the same curve, so it's about 0.55, right? That's what we, it's somewhere 0.5, 0.6, something like that. If you injected from the top, water from the top, and let it drain down, then this is what the breakthrough tangent looks like. So this means that the waterfront saturation is only, I don't know, that looks like about 0.45, somewhere in that range, between 0.4 and 0.5. That's lower. That means that that you're going to be leaving more oil behind. And if you inject upwards, then what happens is that this SWF is higher, and you get more recovery. So it's more like that piston, right? So it's more like the piston. And it sort of makes sense, because if you inject water from the top and it's denser, then it really wants to get down to the bottom faster. So you sort of expect that the breakthrough time to be earlier. If you inject from the bottom and it's more dense, then it's got gravity working to keep it down and to keep it separated from the oil. So it's more of that piston-like behavior where the water is pushing the oil towards the producer well. So we ended the last class talking about capillary pressure. Capillary pressure is something that you would have spent a lot of time talking about in petrophysics. Capillary pressure is the difference between the oil pressure and the water pressure. Okay, really it's the non-wetting minus the wetting pressure, but we're defining it here as the oil pressure minus the water pressure. It is a function of water saturation. And there's two scenarios. There's imbibition. Imbibition is when the wetting phase, in this case water, displaces oil. So that occurs during a water flood. And that curve looks like this. So right here is the residual water saturation. Right here is SW is equal to 1 minus SOR. This is the imbibition curve. And then you have a different curve for drainage when oil displaces water, and that looks like this. So this is this blue curve right over here. This PD is what we call the capillary entry pressure. That is the pressure we need to overcome for the non-wetting fluid to invade the matrix that has water in there. There are some the way you get this, I won't go through the details. You learned in petrophysics experimentally how you determine capillary pressure, but you can fit the data sometimes to a model, like the Brooks-Corey model. Okay, now that might sound familiar to you because Brooks and Corey also have a model for relative permeability, but for capillary pressure it looks like this. That's for drainage, and then there's one for imbibition. And effectively what you do is you find the capillary entry pressure and you fit the curve and find the value of lambda that best fits that. And it's usually above 1, maybe a typical value would be 2 or so. But the point is that we have equations if we need them. You can fit to the data and use those equations. Okay. So you learned a lot about capillary pressure in petrophysics. And so the question is that when is it important? How is it important? How does it affect oil production? Well, there's a few places for that, which I'll get to. But, let me say a few things. One place that capillary pressure is very important is initializing the reservoir. I'm going to explain that at either at the end of today and or on Friday, and Friday we'll do an example problem together. The initialization, the way that works is that because water and oil have different densities, the water pressure increases with depth in a different way than the oil pressure does. And so what that means is that the water and oil pressure, the difference between them, which is the capillary pressure, varies with depth. And because the capillary pressure varies with depth, and because capillary pressure is a function of water saturation, the water saturation varies with depth. Another important part of capillary pressure, as you learn in petrophysics, affects things at the pore scale or the very small grain scale. The way that these fluids interact, it affects how much residual capillary trapped oil there is. And the reality is that the effects of capillary pressure are manifested in the relative permeability curves. So those pore scale effects, although they're affected by capillary pressure, we don't necessarily use the capillary pressure curves. They affect the relative permeability curves. And you probably learned that how much curvature there is in those, what the endpoints are, the endpoint relative permeability of oil and water, and what the residual saturations are, depend on interfacial tension and capillary pressure. Then there is one last case, which is sometimes we do need to directly include the capillary pressure in our simulators. And let me talk a little bit about that. So remember our mass balance. Mass balance on water. This goes back several lectures. We derived that the partial derivative of water saturation with dimensionless time plus dFW, dsW, sometimes I call that FW prime, times dsW dxd is equal to 0. And we have a fractional flow equation that is very general and includes gravity and capillary pressure. With a couple of exceptions, we've mostly been dealing with fractional flow curves that were not including gravity or capillary pressure. Let's look at what FW is with capillary pressure, and just to keep it simple, we'll do without gravity. We could have gravity too, but the fractional flow curve looks like KRO mu O mu. So that's the velocity, and this is the viscosity of oil, dpc dx. I think I did this at the very end of the last plus. I could rewrite this as 1 over 1 plus m. M is the mobility ratio, which is basically the inverse of this, plus k, KRO, mu O, mu, again over 1 plus 1 over m. This is dpc dx, so the derivative of capillary pressure with distance, we can use a chain rule. It's a derivative of capillary pressure with water saturation times the derivative of water saturation with respect to x. Now I'd like to point out that this right here, so this whole equation is with capillary pressure but without gravity. Again, I could have done it with gravity. Just for simplicity, I left that out because we're focused on capillary pressure right now. But this term I've got circled over here is fractional flow of water in the absence of any capillary pressure. So in the absence of any capillary pressure, these terms would be gone and you'd left with that. So I'm going to define this as being FW star. Okay, it's the fractional flow of water in the absence of capillary pressure. So that means that FW is equal to FW star plus FW star times K, KRO, mu O, mu, dpc, dsw, dsw dx. Okay. So this is the fractional flow of water. Remember, FW star is just this 1 divided by 1 plus 1 over the mobility ratio. And if I define a capillary diffusion coefficient, I'll call it D1, which is a function of SW, as being FW star times K, KRO, mu O, dpc dsw. And I take the derivative of this and put it into my equation up here. What I'll get is an equation that looks like this. And I'm going to put it in dimensional form. Okay, so this is my mass balance now. So this was how a D1 was defined. Obviously, if capillary pressure is 0, D1 is 0, and this whole term would go away. If you look, this is in dimensional form, but this is the equation that we've been solving for the last couple weeks. And I'm going to call these the advective terms. By advective, I mean due to flow. Okay, and by flow, there's a velocity there, u. Right? So this is exactly what we would have in the absence of any capillary pressure. And we've been ignoring capillary pressure. If you include capillary pressure, you've got this term as well. This dsw dx term, it's really a second derivative. D1 is a function of water saturation. And I'm going to call these diffusive terms. Okay. So if I don't have any capillary pressure, I get this, and I do exactly what I've been doing for the last few weeks. Now you've got this over here. And what do I mean by diffusive? What I mean is that when we had these advective terms, we had this moving wall, and the saturation would only change because of velocity. Now you have some diffusion, so some spreading that's due to capillary pressure. And the net effect on that is that if you plot water saturation versus XD, remember at a given breakthrough time we normally get something that looks like this. We get this sharp front, right? That's our shock front. But if we do have capillary pressure, what you'll actually get is it'll look more like this. That's a little bit of capillary pressure. If you've got a lot of capillary pressure, then it's even more drastic, and maybe it looks like this. So it's not quite as a abrupt shock front. You've got some diffusion there. And the net effect of that is, unfortunately, that you have early water breakthrough. So as this is moving, this is the first, you know, the water is in front, so you start to produce water a little early, okay, or a lot early. And so that's non-ideal. Just as a very quick review, this was the mass balance on water. This is true no matter what. This is in the dimensional form. The fractional flow with capillary pressure but without gravity looks like this, and I won't go through all those steps again, but you can just do a little bit of algebra and break it up into this way. This is a chain rule. dPc dx is dPc dsw times dsw dx. Then I defined this term right over here as being this FW star. It's the fractional flow of water in the absence of gravity. And then you get this term over here. So if I plug this into this equation up there, you get our traditional equation that we've been solving, our water balance that we've been solving, plus the diffusive terms. Okay, and again, FW star is this, and this D1 is somewhat complicated. I use D for a reason, because it's diffusion or dispersion. We're going to talk a lot about that in the upcoming weeks when we talk about component transport. So an equation like this is going to look very familiar. And the effect of that is as I've drawn over here. The water saturation versus distance. Instead of having this nice abrupt sharp front, you might get a little bit of smearing. More diffusion means more smearing, which means earlier breakthrough, which means less oil recovery. So let's talk about those diffusive forces. Capillary pressure is one of them. There's also other things that can cause this smearing, which are similar. We won't get into that, but there's compressibility of the fluids. Remember that we've really been saying that these fluids are incompressible for our purposes, even though we know that they're slightly compressible. There's actual diffusion and dispersion. Another thing that happens is numerical dispersion in reservoir simulators. Don't want to get into that too much, but the issue is that even if you had no capillary pressure and a lot of these other things, in a reservoir simulator, as you learned in your last homework, you break the simulator up into these big grid blocks. And they are pretty big, because if the reservoir is 10,000 feet long and you have 100 blocks, then that means that each one of these blocks is 100 feet. Okay, that's pretty big, right? That's going to be a third of a football field. Okay, so those are going to be pretty big grid blocks. And when you break that up, you're making an approximation. And because of that, it's very difficult, if not impossible, to get these very abrupt shock fronts, even if you should have one. So in reservoir simulators, you will get some smearing, these smearings, the lack of a shock front, even if you should have one. And that is a long-standing problem with reservoir simulators. The easiest way to solve that problem is to use smaller and more grid blocks, but that's additional computation time. And then there's lots of people that are working on new numerical techniques to minimize that effect. I bring that up because in your homework, I asked you to compare the solution that you get by hand to CMG. And you will get a little bit different answer because CMG, the reservoir simulator, will have a little bit of numerical dispersion and have a little bit earlier breakthrough, a little bit lower oil recovery more than likely. And you'll see that a little bit, but they should be close. So again, these diffusive forces can cause spreading at the shock front. The larger the diffusive term, the more spreading. And then these macroscopic capillary effects, I mean at the large reservoir scale, is important in these cases over here. So this was the question I just had a moment ago, is that how do I know if capillary pressure can be neglected? Well, it's possible on an exam, I'll just tell you, but in real life you'll have to figure that out for yourself. And what you want is that if this number here is less than 3, then you do you do have capillary pressure. It's important, right? And so if L is small, like in the lab, if we have a 1-foot core, then that is probably going to be less than 3. Or if your velocity is small, or if your water viscosity is small. So those are cases where that would be the case. So capillary pressure is only important in these situations here. So one place where the velocity is small is in unconventional reservoirs where the permeability is small. So for the same pressure gradient, you get a much smaller velocity, so U would be small, and that would be less than 3. So at the reservoir scale, the length is much, much greater than a foot. You're less likely to have capillary spreading. You might have other types of diffusive forces. There's also something that's called end effects. End effects are obviously things that happen at the ends of the reservoir. I think common sense will tell you if you go to a big enough scale, then things that happen at the ends are not quite as important. I'm not sure if we'll have time to talk about capillary end effects, but that's something that concerns us when we do experiments in the laboratory for upscaling into field studies. Okay, so I bring that up to say, well, why is capillary pressure so darn important? We talk a lot about capillary pressure in your petrophysics class and in here. So if we have a large reservoir and if that number, that Rappaport-Liais number is too big to matter, then why do we talk about capillary pressure? Well, again, capillary pressure is what causes oil and water to be trapped. That's what causes SOR and SWR. And those effects are manifested in the relative permeability curves. So the shape of these relative permeability curves are affected by capillary pressure at the small scale. And the shape of those relative permeability curves are really, really important because they affect the fractional flow and the derivative of the fractional flow curves, and they dictate all of our equations in our oil recovery. So it's not that capillary pressure is not important, it's very important. It just shows up in this relative permeability curve. Okay. Another very important place is the initialization of reservoirs, which I've alluded to. And I think this is a good time to cover that. So I'll cover that now and in the next lecture as well. And hopefully we can do an example problem with that. So let me talk a little bit about how this works. So reservoirs, hundreds of thousands or millions of years ago, were saturated by water, okay? And source rock contained the oil. And what happens is the oil migrates from the source rock to the reservoir, and then that oil pushes out the water. It's a drainage process because the reservoir, regardless if it's a sandstone or a carbonate or anything else, is initially water wet because it's been saturated by water. So you have oil, the non-wetting fluid, displacing the wetting fluid, water. Oil displaces the oil. It leaves some water trapped, right? That's why we have an initial water saturation. The oil doesn't push all of it out. There's capillary effects at that small scale, and that does that. And then you have this oil saturation. Now, what we want to know is what is the water saturation as well as the pressures at different depths. So if we had our surface up here, call this the surface, I'd draw a little oil rig or a truck or something up there, but I'm a terrible artist, so I'm not going to do that. And then at some depth over here, I'm going to call this the water-oil contact line. And below the oil contact line, we have all water. All right. So this is going to be 100% water. But at the water-oil contact line, that's where you start having oil. Okay. Remember, water is more dense than oil. But we want to know what the pressure of water is, PW, pressure of oil is, and the water saturation. And of course, we know that oil saturation is 1 minus water saturation, assuming we got no gas phase. We also know that PC is equal to PO minus PW, and that is a function of water saturation. So what you might be given is the pressure of water at the water-oil contact line. Okay, so you might know this at a very specific location, WOC. And this is depth, right? This is D, depth. And what I'm going to do is I'm going to plot pressure and saturation on the x-axis. So this is going to be P or on that axis. You might be given that pressure over there, so maybe through well logs or something. Or if this is a normally pressured reservoir, you can calculate the water pressure from the depth, right? So pressure at the surface is P atmosphere plus the density of water times the depth. And so if you were to plot pressure versus depth, it's going to look something like this, right? This has got a slope of rho WG. So, and actually what I should have done is said that PW at all depths is P atmosphere plus rho G times D minus D at the surface, right? So D is equal to the surface depth, PW is P atmosphere, but you can do that at different depths. And if you're at the water-oil contact line, D is equal to DWOC, then you can calculate it there. But the key point is that the water pressure varies with depth because of density and gravity. Now, once you know P at the water-oil contact line, you can determine pressure of oil at the water-oil contact line. PO of water-oil contact. And this difference right here is equal to, sometimes I call it PE, sometimes I call it PD, but it's the capillary entry pressure. Remember what that was? That was on our slide over here. It's this value right over here. This PD or PE, capillary entry pressure, is the minimum amount of pressure that you need for the non-wetting phase to invade the reservoir. So you need this difference in pressure for the oil to get there, and that's why right at the water-oil contact line that's the case. And of course, PO is going to be equal to P of O at the water-oil contact line plus rho oil G times okay. So the density of oil is different than the density of water. And because of that, the slope of this is going to be different. It's probably going to be less, more than likely, right? Oil is usually less dense. And so this has a slope of POG okay. And this difference is going to be the capillary pressure, which is different at different depths. Okay. So right at the water oil contact line, it's equal to the capillary entry pressure. And at the capillary entry pressure, the water saturation is 100%. Okay. But as you decrease that, as the capillary pressure increases, right? As the capillary pressure increases, the water saturation gets lower, and at some point, the water saturation is basically equal to the residual water saturation everywhere. So what you do is, once you've got your water pressure and oil pressure, you can take the difference and get the capillary pressure. From the capillary pressure curve, you can determine the water saturation. So then you have the water saturation at all depths. So now you get the water pressure at all depths, the oil pressure at all depths, and the water saturation at all depths. And then you know your initial conditions.